So next let's discuss constitutional isomers. So constitutional isomers are the compounds with the same molecular formula with different connectivity. So the number of constitutional isomers increases with the carbons increasing. So as you go higher and higher in terms of the number of carbons, you start seeing more and more constitutional isomers. So to give a general justification of the number, so you generally see with three carbons you get only one constitutional isomer. When you have 4 carbons it's 2, and as you start going up and up, when you see for 8 it's 18, when you go 9 it becomes 35, to the level where 15 carbons would lead you to 4000 isomers and 30 carbons would lead you to 4 billion isomers and 40 carbons would lead you to 62 trillion isomers. So this is the number of isomers for any given number of carbons that you can find. So the idea of how to draw isomers for any given structure, so let's take an example of C6H14 and let's try to draw the common isomers that you can find. So the first one is the direct structure with 6 carbons. The second structure is where you have one substituent. The third structure is where you have the substituent in a different position. And the fourth structure is where you have 2 substituents at the same position, and the fifth structure is where you have one substituent on each position. And you can draw other structures as well. For example, you can draw a structure of a longer chain, but notice that this structure here and this structure here are exactly the same. Why? When you name both the compounds, you notice that the long chain is still the same longer chain with the substituent at the same exact position, right? So just drawing it differently does not mean that it doesn't have the same structure. So both of them do have the same structure. So this is how you can avoid them. One way to avoid them is by naming the structures. If you name the structures and you still get the same name, those are not constitutional isomers. So constitutional isomers are compounds with different IUPAC names. So they have different IUPAC names. And this table gives you a reference of number of carbons that processes the number of compounds that you end up with. Let's take a simple example of 2 compounds and see if they are constitutional isomers or not. So let's see, we have these 2 structures here. In these 2 structures, we want to know whether they are different substances or the same substance. So when you find out the longer chain, notice that here the longest chain is 1, 2, 3, 4, 5, 6, 7, 8 and 9. This is the structure that gives you the largest number of substituents. You can go in this direction as well, but that direction will give you smaller number of substituents, so you don't need to do that one. So always choose the structure. If you have the same carbon length, choose the one that has the longest number of substituents. So here this structure will give you the largest number of substituents. So we have 9 carbons. Now look at the substituents that you have. So 1, 2, 3 and 4. So there are 4 substituents here. So let's take a look at the second structure. Now in the second structure, what are the number of carbons that you can find? What is the longest chain? So I'm going to draw the longest chain so that you don't need to again. So 1, 2, 3, 4, 5, 6, 7, 8 and 9. Next, let's look at the substituents. This is 1, 2, 3 and 4. So these are the substituents that you have. So these are the substituents that you have based on the carbons. Now always name in the direction which gives you the smallest number of the substituents. So in which direction will you name here? When you start from here, this gets 3, so you don't want that. When you start from here, it gets 2 here. So start naming this way. So 1, 2, 3, 4, 5, 6, 7, 8 and 9. Next in this here, if you go in this direction 3, if you go in this direction 2. So 1, 2, 3, 4, 5, 6, 7, 8 and 9. Now how do you know that these are different compounds? Is name the compounds. Now in this compound, when you name them, notice that this is an ethyl group, this is ethyl, this is methyl, and the second one is also methyl. Here again methyl, methyl, ethyl and ethyl. So always start with ethyl, right, in the alphabetical order. So here you have 3, 4, 2 ethyl groups are there. So 3, 4 diethyl, and you have 2, 7 dimethyl. So alphabetically di and tri are not counted. We only start with the number, we only start with the name itself, not the prefix, right? Dimethyl, and finally the total number of carbons is nonane. Next, in the second one, you also have 2, 3. So you have 3, 4 diethyl. Next you have 2, 7 dimethyl nonane. Notice that both the compounds have the same name, so they are not constitutional isomers, right? So these are identical compounds. So they are identical compounds. So this is how you can differentiate between constitutional isomers and identical compounds. So let me give you some more examples so that you can practice on your own. So now try these problems. So always remember, the first thing that you want to do is name them and then check whether they are in a particular sequence or not, and then finally judge whether they are isomers or the same compound itself. So if the name is the same, it's the same compound. If the name is different, then they are constitutional isomers. So pause the video right here and try to solve these problems. So next let's talk about relative stability of the isomeric alkane. So we have different isomers, but we want to know what is the one that's going to be more stable. So the one that does not have, so one way of checking the relative stability is by measuring the heat of combustion. So the amount of energy that is released when it combusts in the presence of oxygen. So if you take unbranched alkanes that generally have the highest amount of energy, with the highest branched alkanes having the lowest amount of energy. So the more branched the structure, the lesser the amount of energy that it releases. So the less branched the structure, the more energy it releases. So the more branched the structure, the lesser the energy that it releases. So what are the sources and the uses of alkanes? So various components of petroleum are generally separated by using distillation, and these components are the ones that we use as alkanes. For example, below 20 degrees, any molecule between 1 carbon and 4 carbons releases. That's about natural gas, petrochemicals and plastics. Between 20 to 100 degrees centigrade, between 5 and 7 carbon compounds generally are solvents that are released. Between 20 to 200 degrees centigrade, you end up with gasoline. 200 to 300 degrees centigrade, you end up with kerosene and jet fuel. 200 to 400 degrees centigrade, anything above carbon 12, that is heating oil and diesel. Non-volatile liquids are 20 and higher, that's about lubricating oil and grease. Non-volatile solids are generally wax, asphalt and tar, are generally compounds that are released which have carbons that are 20 and higher. So the gasoline fraction of a crude oil is generally about 19%, which is generally not enough to meet the demand. So one way of increasing the gasoline fraction is by using a method called cracking. So gasoline in general is a mixture of straight, branched and aromatic hydrocarbons which have about 5 to 12 carbon sizes in size. So the large alkanes can be broken down into smaller alkanes by the process of cracking. Cracking is also a process of hydrogenation where you add hydrogen at high temperatures and high pressures. So at that temperatures, a long chain carbon splits into smaller chain carbons. So this straight chain carbons also converted into branched alkanes by a process of reforming. So after this process, the yield is about 47% rather than 19%. So which makes it easier to have much more profitability in the process. Newman projections. So what are Newman projections? So what are Newman projections? So in general, there is one problem with single bonds is because single bonds can rotate. So they can change their structure and rotate. So because single bonds can rotate, they can have different versions of the same molecule, and those versions are called conformations. So we call them conformations. So these conformations can only be understood if we change the way we draw the molecule. So those projections that can represent the conformations are called Newman projections. So we call them Newman projections. So let's take a simple example of a wedge and dash drawing. So let's take a simple example of ethane. If you take a molecule of ethane, you have two carbons on each edge, but the hydrogens are not exactly in a planar structure. When you draw it on a single paper, you can only see 2D structures. So you can only see 2D structures, but you cannot see 3D structures on a paper. So what we do then is we replicate a structural notation to represent a three-dimensional structure. So one of them is wedge dash presentation, so which we discussed in lecture 2 as well, chapter 2 as well. So one of those is, for example, let's say if I draw so when you look at this in this diagram here, so we can write that these are the hydrogens, and on the other side so this is an example of a wedge dash drawing. So what does the wedge dash drawing indicate here? It indicates the three-dimensional structure on a two-dimensional plane. So let's take a look at the exact same molecule in 3 dimension, and you will understand why I drew the structure this way. So the first thing to remember is that whenever you see a wedge, the wedge indicates that it's towards the right. So it's towards you, towards the, sorry, let me write it this way. The wedge indicates that it is out of the paper, and the dashed line indicates that it is going into the paper, and the line represents that it's on the paper, right? So this is how you can interpret the structure. But let's take a look at the three-dimensional structure of a general ethane molecule. So this is the ethane molecule. So this structure represents the molecule of ethane with 2 carbons and 6 hydrogens. Now let's just look at the three-dimensional structure. Notice that this actually represents the three-dimensional structure. In this three-dimensional structure, what you see here is this is the carbon. These are the 2 carbons, and everything in white are the hydrogens. So everything in white that you see here are the hydrogens. Now let's take an idea of how this can be interpreted in any other format. So this structure here, when you rotate this structure, notice that if you look at it as a plane structure like this, on paper you would actually see this structure. But when you actually rotate the structure, you notice that the molecules are in different positions from each other. Because they are in different positions, what we can do now is the carbon that we have, the hydrogens that we have, are represented in wedges. So in this structure that we have, so notice that you have the 2 carbons and the 6 hydrogens. The same molecule, if you want to look at it in a three-dimensional structure, it would look somewhat like this. So this is what the molecules would look like in a three-dimensional structure. In this form, when you look at the actual, notice that here the carbon, and notice this here, these 2 hydrogens. Notice that it's in the same plane. When you look at it in the same plane, carbon, this hydrogen and this hydrogen are all on a single plane. But these 2, one is peaking in the back, one is in the front. Here this is in the back and this is in the front. So to represent this correctly, we use the wedge dash representation. So that is the reason why we use the wedge dash representation. Now let's come back to the idea behind the rotation of the molecule. So when you look at this molecule, focus on the single bond between the 2 carbons. So between the 2 carbons, when you have the single bond, the bond itself, so when you look at the bond itself, this actual bond can rotate. So this rotation of the bond can cause different structures to form. So to represent that rotations, we have to know what is a Newman projection. Newman projection is actually taking the molecule and looking at it in a specific direction. So what we do here, we rotate it 90 degrees and we look at the molecule like this in a direction that's perpendicular to the view, where if you look at the actual molecule, straight molecule side, you notice that there is 2 carbons that are on the same structure, and there is 1 hydrogen on the top, 1 on the bottom, and anything to the left and anything, there is things to the left and there is things to the right. So let me write this in terms of the actual structure. How can we represent this? So when you look at the wedge dash construction, there is one another form of construction that we can do. So it's called the sawhorse projection. So the sawhorse projection actually takes the actual three-dimensional structure and tries to present it on a two-dimensional paper. So this is an example of a sawhorse projection. So now in the sawhorse projection here, we have hydrogen. So these are all hydrogens that we have. And these 2 are the carbons. So this is 1 carbon and this is the other carbon. So what we are doing in Newman and Newman projection is we are looking at the molecule in a certain direction. So here we are looking at the molecule like this. So when you we are looking at the molecule in this direction. So when you are looking at this like this, what is going to happen? So you're going to see a straight line, this line here, this straight line, and this is going to be on the left side, this is going to be on the right side. In the same way, this is going to be on the left side, this is going to be on the right side. So what we can do now is we can draw this as a Newman projection. So how would a Newman projection look like? So how do you draw the Newman projection? So just draw a circle first. So the first thing we want to do before the circle is note down the actual construction or the wedge dash representation that we have. So all of these are hydrogens, and our perspective is like this. So when you look at it like this, remember that this is in one single straight line in a vertical direction. So what we can do now is represent the first carbon as a circle, and when you write the first carbon, the second carbon is not visible because it's in the back. So what we are doing here, basically we are trying to replicate the structure that we had. So when you look at this molecule here, what we are doing, we are trying to convert this molecule that you see here into this exact structure. So this here, what you see here is the Newman projection. So there are two hydrogens on the left, two hydrogens on the right, and the hydrogens in the front and on the top and the bottom. So let's try to write this as a Newman projection. So what we have here is the first one. Notice that the central carbon is right here. So this carbon, the first hydrogen is the top one. So this hydrogen here is this one, hydrogen. Next, this hydrogen is on the right side. This is on the left side. So here, this is on the left side and one on the right side. So one hydrogen and the other hydrogen. Next, we want to draw the backward ones. Notice for the backward ones, because the carbon is covering everything, lines aren't going to be visible until the carbon. So one way of representing that is by not drawing the lines inside the circle but outside the circle. So this is 1, 2 and 3. Notice that this here is on the left side. This is on the right side, and this goes on the bottom. This here is on the top, this on the bottom. So hydrogen, hydrogen and hydrogen. So this is how you can convert a structure into a Newman projection. So let's take some more examples of this and let's try to understand it much better. So let's take different atoms rather than just taking the carbon. So let's say I have a structure that looks somewhat like this. So let's say this is the structure and the view is this way. So we are looking at it like this. So if the observer is right here and if you are looking at it this way, so first thing that you want to do is, based on the wedges and the dashed lines, note down which side is what. So notice that this is a wedge, which means it's on the right side. This is a wedge, which means it's on the right side. This is, if this is the right side, the one that's attached to it becomes the bottom. This here is the top. So one that you see here, if there is nothing at the end, it means that it's a CH3 molecule. Now notice that dashed wedge is not given. So if the dash is not given, so it is hydrogen, right? So remember that it is hydrogen. So which means that bromine is on the right. So the assumption here is that the dashed one is going to be hydrogen, which is going to be on the left side. here this is the right side, so which means that on this side there is a hydrogen which is on the left side. Now let's try and plot it in terms of the circle. Remember that you are observing it in this direction. So when you observe it from that direction, so the first circle, in the first circle write the ones that you actually see in the front direction, only this half. So write this half first. So write this half first. So when this half you have bromine on the right side. Remember that there are two tongs on the left and right and one on the bottom. So always first start with the bottom. So we have done the bottom. Next draw the one on the right and the one on the left. Next write the back side. Notice that one is on the top and there are two on the left and right. That's it. Now write down the molecules on those sides. So notice that this is on the right side. So in this diagram, so just draw a reference line in the actual center. If you think this is the actual center, then this becomes bromine, and on the bottom this is bromine. Next you have other lines as well. So we have CH3 here and CH3 on the top. Notice that this one is this structure, this one is this structure. Next hydrogens on the left, so hydrogen and hydrogen. So this is it. This is how you can convert the structure into the problem, into the structure here. So let's try another example of this so that you understand it much better. Let's say this is the structure that is given and they've asked us to look at it there like this. Now if the mentioning here is that if you're looking at it like this, which means that this one, you need not worry about which is on the left and which is on the right. You can consider any one of them on the left and right, and the one on the bottom becomes the bottom, and on this one becomes the top, and this is the bottom. Here both are attached, so which means any one of them can be left, the other can be right. Right? And here there is nothing there, which means there are hydrogens here. So one wedge is hydrogen and the dash here represents hydrogen. So here hydrogen, this one becomes the right one, this one becomes the left one. So when you draw the structure circle, you have left and right, and then on the bottom. So this is the structure, base structure, and based on the base structure now draw the molecules that are there. Notice that if nothing is there, it's CH3, so it's CH3 here and CH3 here. On the top and bottom also you have CH3 and CH3. Notice that on top and bottom also there are CH3s, and on the last one on the left and right on the back side you have hydrogens. So let's try another example. Let's say if this is the structure given and this is the perspective they are asking you to draw from. So if that's the perspective they are asking you to draw from, so how would you draw the structure? Notice the first thing is wedge. Wedge means it's to the right. This is a dash, which means this is to the left. So notice that this is the plane. So now if that's the plane, this is the bottom and this goes on the top. If there is a wedge chlorine, which means that the dash becomes the actual, so if the dash is chlorine, the wedge becomes hydrogen. If the wedge is chlorine, the dash becomes hydrogen. So this is to the left here and this is to the right here. Now draw the structure, the Newman diagram. So the first thing that we want to do is draw a circle. Notice that in the first one there is two prongs on the upper side and one on the bottom side. So you have a bottom and two on the upper side. And on the back side there is one on the top and two on the left and right. So now we have drawn the base structure. From the base structure now try to draw the chlorine first. So notice the chlorine, one is on the right in the front. Notice that the one completing the dash is the chlorine, first one, and here the left side is the back one. Next you have CH3 on the top and CH3 on the bottom, and whatever is the left is the hydrogens. So this is the Newman projection for that diagram. So now let me give you some more problems so that you can practice on your own. So in this I have done the first one and the second one. So try third, fourth, fifth and sixth. Notice that in this you don't have an ethyl group, you have a propyl, you don't have a methyl group, you have an ethyl group, and there is an ethyl group on the top and on the bottom. So when writing that, write it as CH2CH3 and CH2CH3. Now notice that there is nothing there, which means that this is also CH3. So pause the video right here and try to solve these problems. So next let's talk about conformational analysis. So in conformational analysis, remember that this molecule represents ethane. The angle between the front hydrogen and the back hydrogen, the adjacent front and back hydrogen, is called as the dihedral angle. So because the single bond between them can rotate, which means the dihedral angle can change. So there are two main configurations for ethane. So one of them is the standard one that you saw right now. So where the dihedral angle between the first and the front hydrogen and the back hydrogen is 60 degrees. So this is also called staggered conformation. And this is generally lowest in energy, and this is also the most stable structure. So the idea behind in organic chemistry is that the molecule that has the lowest energy has the highest stability. So remember this principle, that the lower the energy, the higher the stability. There is one another conformation for ethane. So where both the front and back structures look exactly similar and the angle between them is 0 degrees. The dihedral angle is 0 degrees. This configuration is called as an eclipsed configuration. So it is generally the highest in energy and has the lowest stability. Let's call it has the least stability. So the least stable compound, right? So these are the two conformations that you can get. So in terms of the conformational analysis, what is the difference in energy between these two molecules? This is the idea behind conformational analysis. So when you take an ethane molecule here, if you change the dihedral angle towards 60 degrees, 120 degrees and 180 degrees, notice that at exactly 120 degrees you get eclipse configuration again. Again at 0 degrees you get eclipse configuration, 120 degrees you get one eclipse configuration again, and the lowest energies at 180, 60, 60 and 180 again. So the energy difference between the staggered and eclipse conformations is 12 kilojoule per mole. So you can split that and identify that because each hydrogen and hydrogen has an energy of 4 kilojoule per mole when they come really close. So this is how you can analyze based on the structure how much energy it requires. So this happens because each hydrogen does not, both of them are positively charged and both of them are having a heavier size and they don't want to be close to each other. So that's why to make them become close to each other, you are spending about 4 kilojoule per mole of energy to be held in the eclipse conformation. So this eclipse, so because of the electron pair repulsion, so the between the eclipsing bonds, so with this difference of 12 kilojoule per mole at room temperature, 99% of the molecules will be in staggered conformation. So remember this way. So what is happening here? The bonding and the anti-bonding orbitals are generally overlapping. So they don't want to be really close to each other, which means that when you rotate this bond, they are not going to be stable. So because they want to bond. Right? Let's take another example of propane. So propane is a molecule that has 3 carbons. So when you take this molecule and draw the conformation structure, or let me draw it this way. So when you draw the conformation structure for this Newman projection, notice that these are the 2 carbons and the hydrogens are in the front and the back and there is one at the bottom. So this is CH3 at the bottom. So the exact same as ethane. So on the bottom you have CH3. So that's the only difference here. So this is the Newman projection for ethane. What would be, so this is a staggered conformation again. So what would be the eclipse conformation now? So the eclipse conformation, so the eclipse conformation is where there is no difference in the angle between the molecules. So the hydrogens are close to each other. The hydrogen and the CH3 from the back is close to each other and the 2 hydrogens are close to each other. So we know that for each hydrogens to be this close, you need 4 kilojoules per mole and here you need 4 kilojoules per mole. What would be the energy for CH3 and H? So when you take it for propane, so then this energy will change. So which means now how would the structure look like? So in terms of the configurations, these 3 are the general conformations that you can get. So now the energy difference for propane is 8 kilojoules per mole. So if you take the total amount, that is 14 kilojoule per mole, and from that if you subtract 8 kilojoule per mole, that gives you 6 kilojoule per mole. So that is the energy required to keep CH3 and H closer to each other. So this is the conformational analysis for propane. So this is the diagram that you would get, and this also again, all of the staggered ones, all of the eclipsed ones have the same energy in terms of their highest energy or the higher energy structure, and this will be the stable energy structure at 180, 60, 60 and 180 degrees of the dihedral angles. Now what would be the conformation for butane? Let's take a simple structure for butane. So this is the structure for butane. So you are looking at it in this direction in terms of the observer. Notice that this is the bottom and this is on the top. So now when you draw the structure, So notice that the first, on the bottom part there is a bottom here, so draw in reverse. So now when you write down the structures, notice that on the top there is CH3 and on the bottom there is CH3, so everything else is hydrogens. So there are three conformations that you can get for butane. This is called as the anti-conformation. So notice that CH3 is not just a CH3 molecule. CH3 is actually a large structure containing 3 hydrogens here. So it's a large conformational structure. Now there is one another conformation that you can get. There are two other conformations, one main conformation that you will get again. So that would look somewhat like this. So when you look at the eclipse configuration here, you notice that there is one conformation where you would get CH3H and CH3H and HH. So we know that each of these costs about 6 kilojoule per mole. So this is about 6 kilojoule. So we know that this is 4. So when you add 12 plus 4, you get 16 kilojoule per mole. So this is the energy for this conformation. The other conformation that you would get would be the one that's most unstable. So where you would have two CH3s right next to each other, HH and HH. So we know that the total molecule is 16, but we know that each of these is 4. So when you count out 16 minus 8, so the total value would be, so we know that so we want to know the value between two CH3s. So this conformation is called as a gauche conformation. So gauche conformation. So gauche conformation is called as a gauche interaction. So what is a gauche interaction here? Is when you have two molecules that are too big and they are really close to each other, they'll interact together. This interaction can cause high amount of energy to require to become really close together. So this is called as a gauche interaction. So where even though they are staggered, but they are really close because they are too big. So this is an example of gauche conformation. So again, remember that all of these are staggered conformations. Notice that in this structure where you would get for example, if this is CH3 and this is CH3, notice that these two are large structures. The amount of energy required to keep them close together is high. So this type of configuration is called as a gauche configuration. So all others are hydrogens basically. We call this a gauche conformation, and this also has instability, and this also has the highest amount. So the one with the least energy is the anti-conformation. So the structure with the least amount of energy is the anti-conformation. So if you take an anti-conformation, so anti-conformation has the least. So the amount of extra energy that you will have is when you have a gauche conformation, the energy is about 3.8 kilojoule per mole. Eclipse conformation is 11 with the highest, where CH3 and CH3 are right next to each other, and CH3H is 6, HH is 4. So these are the energies that you require. So the total amount generally is 19. So from that, if you take out 8 of each of hydrogens, then between CH3 and CH3 you require 11 kilojoule per mole of energy for them to be kept in eclipsing interactions. So because of the excess strain on the structure. So with this, so this is the idea behind conformational analysis. So hope you understood this. So next let's talk about cycloalkanes. So cycloalkanes are structures with cyclic bonds. So where you have, they form a complete cycle. So the ideal bond angles for sp3 hybridized carbon is 109.5. So if the cyclohexanes were flat, alkanes were flat, each carbon in the ring would experience an angle strain. That angle strain is the energy, that is the angle strain is due to torsional strain, because if the ring was flat, all of these carbon-carbon bonds would be in eclipsing rotamers, meaning that they can rotate, so causing considerable torsional strain. So the combustion data actually shows you how stable each of these rings are. The most stable and the most violent ones are cyclopropane and cyclobutane. All others have reducing energies. So these two are the ones that give you the highest amount of energy with the least amount of stability because of the high energy heat of combustion. So, and all of the rest are very small and they start going down as you go along the table. So notice that as you come down, you start noticing that it's a rapid reduction. So let's start with cyclobutane. So cyclobutane is 227 kilojoule per mole less stable than cyclohexane per CH2 group. So the angle strain between the structures is 88 degrees, and any slight torsional strain results in adjacent CH bonds neither fully eclipsed nor fully staggered, meaning that when you try to bend these bonds, the bond bending can never be too close, can never be too far. So that is the idea behind cyclobutane. Next is cyclopentane. Cyclopentane is only 5 kilojoules per mole less than that of cyclohexane. Cyclopentane has very little angle strain because the bond angle is nearly 109.5. That's why it's generally the most stable one, and it generally has very less torsional strain because it adopts an envelope conformation. So if you look at the original structure of a cyclopentane, it looks somewhat like an envelope. So this enveloping structure is what makes it more stable. Next, let's come to cyclohexane. There are 6 different conformations that you can have for cyclohexane. There is a chair conformation, half chair conformation, twist boat conformation, and boat conformation. The one with the most stable conformation is the chair conformation, is the most stable conformation. Why do you have a chair here? Let's take a look at the diagram and we'll see how it actually looks that way. Why does it look that way? So let's start with a cyclobutane. Let's look at how it looks in 3-dimensional structure. So let's take a look at this cyclohexane. Notice the actual strain. Even though it looks like a square when you look at it in this perspective, when you actually bend it and look at, notice the actual bending here. This is what I mean by the torsional strain, because this bend is what causes the strain in the structure, and this strain can never go away easily. So that's the reason why the molecule is generally unstable. Now let's take a look at cyclopentane. So when you look at a structure of cyclopentane has a structure that looks like a pentagon, but when you bend it in one direction, you'll notice the actual change in the structure. So the actual bends that you see here are the ones that represent the torsional strain. Because the bends are nearly identical on all sides, so it's easier for it to stay in this structure. Now let's look at cyclohexane. So cyclohexane, when you render it into the original structure, it generally looks like a hexagon when you so you'll see like this, but when you bend it in one direction, so when you bend it like this, you start noticing the chair conformation. Let me show you in terms of how it actually looks when you look at it like a conformation. So recognize the conformation now. Notice the structure here. So this is the structure that you generally see as a chair conformation. So this is the most stable conformation for cyclohexane. So this is the chair conformation that you saw there. So how to draw the chair conformation and how to represent the hydrogens on them. So a chair conformation on each of these carbons, when you look at it, this is how you represent the conformation. I'll show you how to draw it. There is no angle strain because the angles are beyond 109.5, and there is no torsional strain because all the adjacent carbon hydrogen bonds are staggered and they are really far away from each other. So they are not in one direction from the other. So all the other possible conformations will have some amount of angle or torsional strain. That's the reason why this is the most stable structure of cyclohexane. So this would be the Newman diagram. Notice the hydrogens being far away from each other. Because they are far away from each other, they can have enough of a structure. Now let's try and understand how to draw the cyclohexane conformation. So the first thing that you want to do is draw a line, a slanted line like this. So let me draw it with a different color. So first draw a slanted line. Next draw a V shape in such a way where, so draw a V, a wide V. Now draw another line. That line should be parallel to this line. Next, draw another line starting from here that should be parallel to this line. Next, draw the line between these 2 points that's parallel to this line. So this is the cyclohexane structure. Now how to draw the hydrogens? So all the ones that are on each structure, when you draw top and bottom, alternate the structures. So if you start with here, one on the top here, then here it's on the bottom, top, bottom, top, bottom. Next, if you want to draw the rest of the hydrogens, the next one we want to do is how to draw the lines here. Now draw the line parallel to this line here. So let me draw it this way. So the line that you want to draw here for this carbon here is this line. So basically draw parallel to that line. Now the same thing with this carbon as well. So draw a line here parallel to that line. Next, come to the down part right here. For this one, draw a line parallel to this line. The same thing with this one as well. Now, the next one we want to draw is the one for these 2 carbons. So this carbon and this carbon here. So draw a carbon parallel to this line for this carbon here. The same thing with this carbon here as well. So notice the colors and notice the carbon where you're drawing them. If you're able to draw this way, it makes it easier to understand where to draw each of these ones. And just write down the hydrogen. So this is how you draw the chair conformation. So let me draw it again so that you understand it better. So start with a wide V first. Next, draw 2 parallel lines at an angle. Next, so let me draw it with different colors so that you understand it better. So the line you draw from here should be parallel to the blue line. Next, the dry line you draw from here should be parallel to the red line. That's it. Now, how to draw the hydrogens now? So first, vertical lines start from the top right corner. In the top right corner, vertical, and then alternate the structure. So if it's on the top, the next one is bottom, top, bottom, top, bottom. Next, start with the other hydrogens, starting with the top right corner again. Draw the line parallel to the red line. and on the bottom as well. Draw the line parallel to the red one. So because this is on the top, the other one will be on the bottom. So whenever you alternate the structure, so you have to understand, one is on the top means if it's on the top, the structure in the next line you are going to draw is on the bottom. If it's already on the bottom, the next line you're going to draw is on the top. Next, once you draw the red line done, next on the other two carbons, these two carbons, draw the line parallel to the blue one. So blue and blue. Next on the last one, draw the one based on the other two lines. So these are the other two lines. So this is one line and this is the other line. So for this line, so for this carbon here, draw the line parallel to the green line. So because it's already on the top, this one on the bottom, this is on the bottom, this is on the top. That's it. So this is how you draw the structure. Next, label everything as hydrogens. This is how you can draw the structure for cyclohexane in its correct conformation. So this here is the chair conformation for cyclohexane. Now, so once you have done the conformation, the chair conformation, let's try and understand what each of these mean here. So when you drew the structures, we drew two types of hydrogens, ones that are on the top and bottom and ones that are on the sides. So we drew ones at an angle. So the ones that we drew at an angle are this one, this one, this, 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 this. All the ones, whenever you draw a cyclohexane structure, so you draw one on the bottom and the one on the side. So this position is called as the axial position, and the one you draw with an angle is called as the equatorial position. So the one you draw on top and bottoms are called the axial position, and the one you draw on the at an angle is called as the equatorial position. So once you know the axial and equatorial positions, it makes it easier to understand how the structures are. So let's try an example of this and let's try to draw a structure of a given compound. So let's say there is a cyclohexane. So they are asking us to write this as a conformation. So first things first, write the conformation in its conformation structure. So we drew the conformation. Anything that's directly written, always write it on the top. That's it. So this is the conformation for this structure. Now when you change the conformation, when you rotate this, how will you rotate this? When you rotate the structure, meaning that if this comes here, what will happen? When you rotate the conformation, axial changes to equatorial. So what happens here? This structure, when you flip it, it becomes somewhat like this. So when you rotate the structure, the one that's, so it's still on the top, notice that this is the plane, so it's still on the top, meaning that it's still on the top, but this time in the equatorial position. So when you rotate the conformation, you change it from equatorial to axial. So you're basically flipping this structure from top to bottom. So you're pushing it this one here and you're pushing this to the top. So you're basically flipping it. When you flip the structure, this is the conformation that you end up with. So try one another example and let's try and draw both conformations for that. So this is the structure that they've asked us. So I'm going to draw the first conformation. So in this structure, notice that this one becomes the axial position. So OH. Now try to draw the second conformation. So what we are doing here, this one comes here and this carbon goes here. So when you draw the second conformation, notice that you change the basic structure, you are basically flipping it on the other side. So now this one in the axial position, it's still on the top, so which means this is going to begin the equatorial position. So this is the conformations that you do have for the positions that we have. Now how to draw the Newman projection for this structure? So one way of looking at axial and equatorial positions is you don't require every single time to draw the axial, equatorial and the positions correctly. So just know that this is how you can flip from axial to equatorial positions when you flip the conformation. So when the diagram is to the right side, you can draw OH on the axial side. So when your diagram is to the left, leaning left, then OH becomes the equatorial structure. Now we drew the two conformations. Now which one is stable? So this is the question that we have to answer. Between the two conformations that we drew here, which one is stable? So when you take a look at the actual diagram, so you notice that the conformation where you have the one in the equatorial position is generally the one that generally be the more stable one. The reason is because of steric interactions. What is a steric interaction here? Is when you look at the hydrogens that are there, they are close to a really large atom in the axial position. But if it's in the equatorial position, they are really far away and they can never be interacting with the compound. So because of this reason, monosubstituted cyclohexanes, the monosubstitution is always going to be stable in the equatorial position than in the axial position. So this is the difference here. Next, let's take a look at disubstituted cyclohexane. So when you have multiple substituents, so which represent solid or dashed lines are generally used to show positioning of the groups on the ring. So for example, here they have mentioned a cyclohexane with chlorine as a dash and methyl on the dashed line. So let me write it down separately here. So when you draw the chair conformations, wedge represents the top, dashed represents the bottom. Right? So top or up, bottom or down. Right? So when you write down the chair conformation, how will you draw the chair conformation now? Now, so notice the chlorine is on the top. So there are only two things at each position. So if you draw the one on the top, so at each carbon here, the top represents one is axial, the other is equatorial. So for example, if I consider here there is a top part here, if there is an axial position here, then anything that is here will be, the axial will be at the bottom. The same way, because the axial is on the top, the equatorial will be on the bottom. Here axial is in the bottom, equatorial will be on the top. Now based on this understanding, now chlorine here is as a wedge, is written as a wedge, which means it's on the top. So this is the chlorine, and methyl here is written as a dashed line, which means it's at the bottom. Or methyl, let me write it, Me. So whatever is left is hydrogen there. So notice that you don't need to write every single time, every one of them. So just write it as this structure. Now what would be the other conformation for this? The same structure here. So what would be the other conformation for this exact structure? Would be to flip it. So where this would come here. So this would come here and this will go here and methyl will come here. Right? Notice that now when you draw the structure, now let's take a look at the structure. Notice that if this is on the top here, it will become equatorial, chlorine here. Next methyl, it's on the bottom, it will become axial. So it will axial, now it becomes equatorial. So equatorial meaning that now it should be parallel to this line here. So now notice that if this is on the bottom, this is on the top here, which means there is one like this here. So this is methyl. So you don't need to draw the axial every time, just know that if one is axial, the other becomes equatorial. So this here is the stable conformation. So when you draw the conformations, always start with the unstable one and then draw the stable one, so that it becomes easier to understand how the conformational structure generally works. So this is how you can draw a disubstituted structure. So for example here it's hydrogen, hydrogen. So it will become hydrogen, hydrogen. So basically we are changing axial to equatorial, we are changing their positions by changing the conformation. Now try something on your own, try another one on your own. So try this one. So ethyl and a methyl group. Let's try, so let me do this one, I'll give you the next one. So this is the chair conformation. So the first thing we have done. Now ethyl is a wedge, which means it's on the top. Methyl is a dashed, which means it's at the bottom. So we start here as 1, 2 and 3. So this becomes number 1. So ethyl is on the top. Remember that we are drawing here on the top here on the side. So top, side, and on second carbon, one is on the top, so this becomes the bottom, up. Next, this becomes top and then bottom. Now draw the structures. So notice that this is on the up and this is down. So notice that at each of these draw a horizontal line so that you know which is up, which is down. So here it's up, so ethyl here, and whatever is left is hydrogen. So on these two places there's hydrogen, and this is the third carbon. On this carbon methyl is down and hydrogen is up. So this is how you can draw the structure. Now notice that ethyl is a large structure in comparison to methyl. Notice the position in them. This is in the axial position, this is in the equatorial position. This is a really large structure, so it should be in the equatorial structure. So what we do now is change the conformation. So push this here and push this here. So what's going to happen to the conformation now? So let me draw it in a separate page so that it becomes easier. So now in this structure, notice that ethyl was in the axial position, so in this structure it should be equatorial. Equatorial, bottom, top, bottom. So we are only concerned with 3 carbons, so I am not going to write every single one of them. Now, based on the structures, this was on the bottom and equatorial, so it becomes in the bottom and the axial. So methyl will come here. So methyl will come here, ethyl will come here, and everything else is hydrogens basically. So this is the stable conformation. So let me give you some more practice problems so that you can try them on your own. So try these structures one by one, and in G here, Just take this as an entire structure itself. Notice that this is isopropyl. So this is isopropyl and this is also isopropyl, and this here is a terbutyl structure. So take it accordingly and try to draw the chair conformations for each of them. Remember that, try drawing both conformations and represent which one is the stable conformation. So try this on your own and see if you can solve them, and we'll review this when we do in the next live session. So next, let's talk about cis-trans isomerism. So what do you have here in terms of cis-trans isomerism is when naming a disubstituted cycloalkane, so we use the prefix cis when you have two groups on the same side of the ring, and trans when the two substituents are on the opposite sides of the ring. So if this is the ring structure, if CH3s are on the top, we call it cis structure, and both of them are on the opposite sides, we call this the trans structure. So when you write it as a chair conformation, both of them will be in the same upward direction. It doesn't matter that both have to be in axial. If both of them are in the same direction up, then it means that it's a cis direction. So notice that these two represent the cis conformation. These two here represent the trans conformation. So these two represent the trans conformation and how it works. So let's try some examples of this. So finally, let's talk about the last topic, polycyclic system. So decalin is a structure which is a two-membered to six-membered rings fused together. So if one structure is downward in comparison to the other structure, we call this the cis decalin, and if both of them are next to each other, we call it the trans decalin. The reason we write this is based on the hydrogens where they fuse. So if the hydrogens where they fuse are on the same side, we call it cis decalin. If the hydrogens where they fuse are on the opposite side, we call it trans decalin. So the decalin is the substructure of many of the compounds such as steroids. Notice that in steroids, you notice the structure here. This is a decalin base structure built on the testosterone. Most of the steroids are built on this base structure. There are many important structures that result when more than one ring is fused. One example is bicycloheptane. It's also called norbornine. Camphor is an example where it uses bicyclo structures. Camphene also uses the same. These are generally the fragrant natural products that you can isolate from evergreens. So one other example of a polycyclic system is diamond. So a diamond is a network of six-membered rings that are fused together. The six-membered rings are carbons. All of them are carbons that are fused together. So this fusing causes it to become stronger and lighter. So this is the idea behind polycyclic systems. So with that, we end chapter 4 on alkanes.